Hi, let's use synchronous rectification in our buck converter design in order to increase the efficiency. So the first thing that we have to do is to replace the Schottky diode with this MOSFET. In this case, for simplicity, I'm going to consider the same type of MOSFET we have here, and the configuration is the one of the previous videos. The only difference is that we are going to consider this new parameter, dead time, which is the dead time we include in the control signal of the second MOSFET. We will talk about that in a couple of minutes. So the target for this video is to see how we implement the control signals of both MOSFETs and check if the waveforms we obtain they match with the theoretical explanation. Well, so regarding the control signal of the main MOSFET, I have to say that there is no difference with respect to the previous implementation. Basically because the control signal we have to use is the same. So the circuit and the configuration for this voltage source is the same of previous videos. The new thing is the control signal of the second MOSFET, SV. So here you can see our target. We want to generate this blue waveform. As we explained in the previous video, when the control signal of the main MOSFET is on, the control signal of the second MOSFET must be off. Then we have a dead time interval in which both waveforms are off. Then we activate, or we want to activate, the second MOSFET, and then we have another dead time interval in which both waveforms are off. So how we do this in LTspice? So here you can see my approach. This is the circuit and this is the configuration for this voltage source. Let me explain the values we use for this configuration. V initial is the voltage in low state. So here we want 0 volts. V on is the voltage in high state. I choose 12, but you can use 10, 15, something like that. So here, in my case, I have 12. Then we have time delay. In this representation, time delay is this. So is the amount of time between 0 and the rise of the control signal. Let's choose the value we have to put. So we know that this interval is d times the switching period, and this interval is a dead time. So the value that we have to put here is d, let me put this, d times the switching period plus the dead time. Okay, I use the switching frequency, 1 over the switching frequency, but it's the switching period. It's the same. Okay, then we have the rise time and the fall time. You have to choose a small value, as we previously explained. And then we have T on. T on is this time. So let's choose the value for this T on parameter. We know that this time interval is 1 minus d times the switching period, but that interval is different to this one, because in the bottom time interval we have to include this dead time and this dead time. In this implementation, for simplicity, we consider that both dead times have the same value. So, taking that into account, the value that we have to put here is this one. 1 minus d times the switching period, or divided by the switching frequency, minus 2 times the dead time, because we have to consider both dead times in that part. So with this we finish, because the last point is very simple, it's the period 1 over the switching frequency. Well, now let's see how we choose the particular value of the dead time parameter. I will show you a process that I follow in LTspice. It's just an example. There are more options that you can follow. So here we can see the control signal of the main MOSFET and the control signal for the second MOSFET. And I start the analysis or the process with a very high dead time value. In this case, you can see the results when the dead time is 1 microseconds. Remember that my switching period is 10 microseconds, so that dead time is a very high value. And what we have to do is to check the voltage across the new MOSFET, because in that voltage waveform you will identify the activation of the body diode. Okay, in particular, during a part of the dead times you will see that the voltage across that MOSFET is more negative. Why? Because in that part you have the body diode, the body diode activation, and you see the forward voltage drop of that body diode. In the case of this MOSFET, that voltage is around 0.7 volts. So the voltage that you see in those intervals is minus 0.7 volts. Then the voltage gets closer to 0 because you activate the MOSFET, you have the on resistance, and the forward or the voltage drop across that resistance is smaller. So what is our target? We know that according to the previous video, we need a dead time that must be high enough to ensure that we activate the second MOSFET after the first one is completely off. Okay, we need to wait for the turn off transition and then activate the second MOSFET. So in principle we want a high value, but at the same time we want to minimize the dead time because we want to minimize the conduction losses penalization of the body diode activation. Okay, because during those parts the body diode is driving the inductor current and the conduction losses rises. So we want to minimize that time in order to maximize efficiency. So the process that we follow is we start with a high dead time value and we reduce it a little bit, and we check the waveform and we check how much time the body diode is activated. And you will see that there is a point in which you will see that the amount of time is negligible, and if you continue reducing the dead time, what you will see is that the efficiency falls, because you will reach a situation in which both MOSFETs are activated at the same time, something like this. And you will, if you check the current, you will see a high current flowing into both or through both MOSFETs. Okay, so if you follow this process, what you will the result that you will obtain will be something like this situation, in which the dead time value is around 180 nanoseconds. Okay, it's a value high enough to ensure that you turn on the second MOSFET after you turn off the first one, and at the same time is very small in comparison to the switching period. Probably if you use 160 nanoseconds it will work, but I think that this optimization is good enough. Okay, as I said, if you continue reducing that dead time, you will reach a situation in which you will see a high current peak through the MOSFETs during this transition, and it means that your data is not high enough to ensure that the turn off process has finished. Okay, as you can see in this situation, the body diode activation that we have here is negligible. Okay, so you can work with 180 nanoseconds, 200 nanoseconds, 220 nanoseconds, something in that range. Well, once we choose the value for the dead time, let's see the main waveforms we have in this circuit, and let's see if we validate a theoretical analysis we have performed previously. So first of all, as we always do, we can evaluate the output voltage. Okay, as you can see here, it seems that is close to 3.3 volts. We can check the waveform with more detail, as we always do, like this. Note that here we have 3.31 and here 3.29. The average value is the target output voltage, and you have this peak-to-peak output voltage ripple at, if you check the value, is close to our target. Then we can check, for instance, the current through the inductor, the output current. You will see that the average value of the inductor current is equal to the output current. You will see that during state number 1, the current through the inductor rises. In state number 2, the inductor current falls. You can evaluate the peak-to-peak current ripple and check that is very similar to the theoretical values. Another main waveforms we can check, the control signal of the main MOSFET and the voltage across that MOSFET. So that is what we evaluate here. Here we have the control signal of the main MOSFET, and here I evaluate the voltage across that MOSFET. In this part we want to turn on the MOSFET, so as you can see here, what we have is something close to a short circuit, is the on resistance, the voltage is close to 0, and in this part the MOSFET should be off. What we see here is an open circuit that is blocking the input voltage. If you want, we can replace the control signal waveform with the current through the MOSFET. So in the bottom waveform is the same, voltage across the MOSFET. In the top waveform is the current through the MOSFET. Here we drive the inductor current, here the current is 0, and as in the case of previous simulations, we have here a current peak during the turn-on process, and this is because of the reverse recovery of the body diode of the second MOSFET. We will talk about that in the next video. Okay, let's do the same for the second MOSFET. Here you have the control signal of the second MOSFET. Here you have the voltage across that MOSFET. Here the MOSFET should be off. As you can see, it's an open circuit that is blocking the input voltage. Here the MOSFET must be on. As you can see, the voltage is close to 0, so we know that it's working as a small resistor. Again, we keep here the voltage across the MOSFET, and we represent here the current through the MOSFET. Note that we represent the current flowing from the source to the drain. So here the current is 0, here we have the inductor current. And in this case, when we turn off the MOSFET, what we observe, or what we see, is the reverse recovery of the body diode. We see a negative current peak. It's the same current peak that we saw in the case of the main MOSFET during the turn on. Okay, and finally, we can evaluate input power, output power, and efficiency to see if we improve the results of the previous design. So, as we always see, the output power is constant, the input power is a pulse waveform, and we can use LTspice to get the average value. The average output power is around 50 watts. the average input power is around 52.4 watts. Okay, so we have the power losses we have are around 2.4 watts, very small in comparison to the 6.6 watts of the design with the Schottky diode. As a consequence, if you evaluate efficiency, you will see that it's higher than in the previous cases, and I think that is around 95.4%. So, as you can see, with the synchronous rectification, we have solved or improved or alleviate the problem we have with the conduction of the Schottky diode. Well, so with this, we finish with this video. In the next video, we are going to see where we have the power losses in this design. So, see you